Hello, my name is Björn Askeland. In this video, I'm going to show you how Fourier transform of a complex valued pulse has been used to prove Riemann's hypothesis from 1859. Put on your Riemann glasses and join me in the search for zeros hidden in an ocean of infinity. You probably wonder if a proof on YouTube can be serious. Yes, the proof is serious. The fact is that mathematicians are so afraid of the problem and the solution that I don't think anyone can get a proof published. As you can see in the slide, the editor is recommended by the referee to shy away from publication. If you are interested in the problem, you should absolutely watch this video. The proof can be understood by anyone with a good background in Fourier transform. With around 25,000 universities in the world, this is a solution which is available to a lot of people. This is David's battle against Goliath, but I'm bringing with me a good weapon, the idea. Keep watching. This is the complex plane with a real axis A and an imaginary axis B. The complex number is S equals A plus JB. When the real part A is larger than 1, the zeta function is defined as a sum of complex numbers as shown in the figure. In this area, the sum converges and can easily be calculated. If you move into the blue area, the sum of the length of the vectors is infinite. Riemann managed to express the zeta function in the blue area as an analytic continuation with the formula as shown in the blue area. In order to keep things simpler, I have simplified Riemann's functional equation as zeta s equals A of s multiplied with zeta 1 minus s, also seen in the blue area. Riemann's hypothesis is to show that the functional equation can only be factorized on the critical line where A equals 1/2. While mathematicians are trying to solve Riemann's functional equation, I'm going to work on the original equation. I will use Fourier transform to change the sum into a functional equation with a condition. A zero then means that the zeta function is an infinite loop which returns to the beginning. The sum of the lengths of the vectors is infinite, but the loop is in some manner closed. It's amazing, but then I get the necessary tool which solves the hypothesis. The 3 steps in the proof are: Step 1. Show that the zeta function according to the original definition as a sum can be expressed as shown in the slide. As you can see, it is similar to Riemann's functional equation, but it has a condition. In order to comply with Riemann's functional equation, the condition has to be 0. Step 2. Show that the condition can be 0 only when A equals 1/2, which is the critical line. Step 3. Although a proof is already given in step 2, show that the condition is 0 for all possible zeta zeros. Equation 1 is the Fourier transform from the reference given at the end of the video. Since I prefer time in seconds and frequency in hertz, I use the Fourier transform given in equation 2. The g of t function can be seen behind the integral sign. I multiply the time function with a train of delta functions. In equation 4, I set f to 0 in order to find the sum of the samples. As you can see from equation 4, the pulse contains the zeta function 2 times plus the sample at t equals 0, which is small g of 0. In the frequency domain, g of f is convolved with a train of delta functions. The result is the repeated spectrum in equation 3. And the sum of the samples of the time domain is found at f equals 0 in the frequency domain, which is the sum of g of minus k. In this slide, I just replaced the g of minus f expression with the correct expression for g of f. In equation 8, I replace a non-zero expression with a of s. A of s changes equation 7 as shown in equation 9. In equation 10 I use symmetry to sum from 1 to infinity. Then the sum sign is replaced with 2 times zeta 1 minus s. Next I move g of 0 over to the right hand side. Then I divide by 2 and I get the expression for the zeta function as a sum in equation 11. We are now done with step 1, which was to show that the zeta function as a sum is a functional equation with a condition. It is the condition which solves the hypothesis. Step 2 is to prove that the condition is 0 for a equals 1/2. Then I need to find a different way of expressing small g of 0. I use the area property again. Small g of 0, the sample taken at t equals 0, is the integration of the g of f function. In equation 15, I use symmetry to integrate from 0 to n. This is just simple integration. I end up with equation 19, which I keep for later. The second term of the condition is large g of 0, which is found as an integration of the small g of t function in the time domain. Again, I use symmetry to simplify the calculations. Large g of 0 is completed in equation 25. Next step is to fill the small g of 0 and large g of 0 expressions into the condition of equation 26. Then I get equation 27. Since 2 times a of s is a non-zero function, I remove 2as from the equation. Then I end up with equation 28, which can only be solved when the real part of the exponents are equal. Then the real part of 1 minus s is equal to the real part of s, and with s equals a plus j times b, this easily solves to a equals 1/2. The condition can only cancel when the real part of s is 1/2. The zeta function can only be factorized when the real part of s is 1/2. Which is a proof of Riemann's hypothesis, solved in just 32 equations with Fourier transform. In step 3, I will concentrate on the b-values, the imaginary part of s. It seems necessary to show that the condition is 0 for every factor of the functional equation. In this slide, I first check that when the real part of s is 1/2, the magnitude on both sides of the reworked condition are the same. The verification ends on the next slide. As you see, when the phase expressions are removed, the magnitudes are the same on both sides. The vectors become infinitely large when n goes to infinity. So we have two vectors with a length which goes to infinity with the square root of n. The vectors are also complex conjugate vectors with angles as shown in the picture. The vectors must only rotate 180 degrees or pi radians in order to pass each other again. Since the phase is mainly determined by the e to the natural logarithm of n, an infinitely small change of b is necessary in order to change the phase with pi radians. I said, an infinitely small change of b is necessary to cancel the condition again. This slide shows the phase of equation 35 with the change of b when n equals 1000. The green dots show the locations where the two vectors have the same phase. It is necessary that the green dots match the factors of the functional equation in order to get the zeta 0. This is not the case for n equals 1000. The distance between the green dots are too far. The first Riemann zeta 0 is at approximately b equals 14.1. The condition is clearly not 0 for that b value. We have to increase n. The only difference between this plot and the previous one is that n is now 1 billion. As you can see, the distance between the crossings are now smaller. The green dot is now closer to 14.1, but there is no guaranteed match. We have to increase n. As n goes to infinity, the phase natural logarithm of n times b approaches a vertical line. Only an infinitely small change of b is necessary for a phase change of pi radians, which creates a new phase crossing. The distance between zero crossings then goes to 0. This means that there will always be a perfect match between the factor of the functional equation and the phase crossing as n goes to infinity. A red dot is the b location where phases do not cross. The condition is infinite and the zeta function is infinite. Every zeta 0 must have a corresponding green phase crossing for the same b value in order to be 0. This will always happen since the distance between every green point is 0 as n goes to infinity. But every green point has two red neighbor points where the condition is infinite. For this case, the zeta function is infinite. All neighbor points of a zeta 0 is infinite. All zeta zeros are therefore extremely sensitive with respect to an infinitely small change of the b value. Conclusion: Riemann's hypothesis is true. All zeros lie on the critical line. Riemann's functional equation hides the zeros well. A better way of describing the zeros is to use the following equation. In this equation, a zeta 0 is an infinite loop of vectors which return to the beginning. The condition consists of two infinitely long vectors which can only cancel when the real part of S is 1/2. The equation is then functional and can be factorized with exactly the same equation as Riemann's functional equation on the critical line. This is the Fourier transform pair responsible for a solution of the hypothesis. Well, that's all. If you are still with me, thanks for watching.